So now let's establish what chromatography actually is and look at its core principles. So looking at the basic definition, chromatography is an analytical technique that we use to separate the individual components of a mixture. The separation happens based on the differences in their rate of movement. So to make this separation occur, the mixture is carried by a mobile phase as it travels through a fixed stationary phase. Because different chemical components interact differently with these two phases, they travel at unit speeds and naturally pull apart from one another. This makes chromatography an incredibly versatile and widely used tool across science labs to separate, identify, and purify chemical components hidden within the complex mixtures. Next, there are a few essential vocabulary and metrics needed to measure and understand our chromatographic results. So the first major term is RF value or retention factor. We calculate this by dividing the distance traveled by the substance per the distance traveled by the solvent front. It gives us strict numerical scale. So an RF value of 0 means that the solute is completely immobile and did not move at all, while an RF value of 1 means that the solute moved perfectly alongside the solvent front. Next, we have retention time. Retention time simply means that the total time it takes for a sample to travel completely through a column to reach the detector. Finally, we have the term that describes the washing process itself. Elution is an actual process of washing solute through the stationary phase via the movement of the mobile phase. The eluent is the carrier solvent that we feed into the system, and diluate is the final mobile phase liquid exiting the column at the end of the process. Moving on to another point, let's take a closer look at the system layout by exploring the two essential phases that make chromatography possible. So every system relies on stationary phase and a mobile phase that working against each other. So the first one is stationary phase. Stationary phase is a solid fixed phase that remains entirely in a place and works to absorb the moving component that we are trying to separate. The common examples of materials used for stationary phase is silica gel, alumina, or cellulose paper. Second one is mobile phase. Mobile phase is fluid, either a gas or liquid, that continuously flows over the solid stationary phase, carrying our target mixture along with it. Depending on the setup, examples of the mobile phase include organic solvents or specialized carrier gases. The continuous interaction between the stationary phase pulling back and the mobile phase pushing forward is the exact engine behind the chemical separation.
Now, let's discuss the separation mechanism used in chromatography. There are two main mechanisms, partition chromatography and adsorption chromatography. In partition chromatography, separation occurs because compounds distribute themselves between two immiscible liquid phase. Components that are more soluble in the mobile phase move faster, while those that prefer the stationary phase move more slowly. In adsorption chromatography, separation is based on the adsorption and desorption of compound on a solid stationary phase. Components that are strongly adsorbed to the stationary phase move slowly, while weakly adsorbed components travel faster. Polarity also play an important role. In adsorption chromatography, polar components interact more strongly with the stationary phase and therefore elute later. Non-polar compounds interact less and elute earlier. Next, let's look at the main types of chromatography. The first type is ion exchange chromatography. It uses resin bit with charge group as the stationary phase and a buffer solution as the mobile phase. This technique separates ion based on their charge interaction. The second type is column chromatography. In this method, an adsorbent such as silica gel or alumina is packed inside a column. A liquid solvent moves through the column by a gravity or pressure. Carrying the simple component is separating them. The third type is planar chromatography, which include paper chromatography, a thin layer chromatography, or TLC. It uses a flat surface coated with an adsorbent. The solvent moves across the surface by capillary action, causing the component to separate. Thin layer chromatography or TLC is a type of planar chromatography commonly used to separate non-volatile mixture. The stationary phase consists of a thin layer of adsorbent material, usually silica, gel or alumina, coated onto a flat plate. The mobile phase is a solvent that moves up the plate through capillary action. The separation occurs because different compounds interact differently with the stationary phase. Compounds that are strongly adsorbed move more slowly, while compounds with weaker adsorption move faster. Since silica gel is polar, polar compounds bind more strongly to the stationary phase and have lower RF value. In contrast, non-polar compounds travel further with the solvent and have higher RF value. Now, let's go through to the basic steps involved in thin layer chromatography. First, the TLC plate is prepared by coating it with silica gel and activating it through heating. Next, a pencil line is drawn near the bottom of the plate to serve as the origin line. The sample is then applied onto the origin line using a capillary tube. After that, the plate is placed inside the developing chamber containing the solvent. The solvent reaches up the plate by capillary action, carrying the sample component with it. This process usually takes between 10 and 16 minutes. Once the solvent has traveled a sufficient distance, the plate is removed and the solvent from in market immediately. The separated spots are then visualized using methods such as UV light, iodine vapor, or anhydrine spray. Finally, the RF value is calculated by dividing the distance travelled by the compound by the distance travelled by the solvent front.
Hello everyone, my name is Muhammad Amir Irfan Bemandi. Today, I will be taking you through the expected result, phase systems, and real-world applications of chromatography. Starting with the LC expected results, the core principle driving this separation is light dissolve like. In a standard normal phase setup, non-polar compounds favor the mobile phase and travel further up to the plate, while polar compounds adhere strongly to the silica stationary phase near the bottom. We quantify this movement using the RF value, which is the distance traveled by the spot divided by the distance traveled by the solvent front. An RF value close to 1.0 indicates a highly nonpolar substance, whereas a value closer to 0.0 signifies high polarity. By comparing these values to known standards, we can identify our unknown component with precision. Moving on, choosing the right phase system is critical to achieving a clear separation. In normal phase chromatography, we utilize a polar stationary phase, like silica gel, paired with a non-polar solvent. This causes polar compound to stick to the plate longer while non-polar compounds elute first. Conversely, reverse phase is the exact opposite. It uses a non-polar stationary phase, meaning non-polar compounds are retained longer, allowing polar compounds to pass through first. Understanding this relationship allows us to manipulate the elution order based on specific target molecules we want to isolate. Because of this versatility, chromatography has massive wide-ranging applications across multiple industries. First, TLC paper chromatography are widely utilized in food science and pharmaceuticals to identify food dyes, check drug purity, and detect pesticide residues. Second, column chromatography is the go-to technique in biochemistry for purifying proteins and isolating bioactive natural products from plant extracts. Finally, ion exchange chromatography plays a vital role in heavy industry for water softening and removing toxic metal ions from industrial wastewater. In conclusions, chromatography is far more than just a standard laboratory exercise. It is an indispensable analytical tool through precise physical fingerprints like RF values and retention times. It gives scientists the power to verify substance identified with absolute certainty. From hospital diagnostic to environment, all protection and quality control, it ensures safety and consistency on a global scale. That concludes my part of the presentation. Thank you so much for your time.